Hello everyone, and welcome back to Total Organic Chemistry. This video I'm going to be doing another sort of review of general chemistry. This time we're going to focus on acids and bases and the different definitions and properties of them. Before we get into acids and bases, I'm going to do a little quick review or a quick introduction to curved arrow notation. And curved arrow notation is very, very prevalent throughout all of organic chemistry, and we will be using it for the entirety of this channel in this course. Curved arrow notation is another sort of formalism that shows us where the electrons move, which bonds are being created and broken throughout the course of a chemical reaction. And again, because it's a formalism, it doesn't necessarily show the exact nature or the truth of how these electrons are actually behaving, but it's very useful for determining different mechanisms, comparing and contrasting how chemical reactions occur. So we can have a couple of different examples here. If we have hydrochloric acid, we can show that breaking or taking the hydrogen off by moving this bond to the chlorine. And I've used these curved arrows before in previous videos, but what this means is that that pair of electrons in the chemical bond are moving. Instead of being between those two atoms and forming a bond, they're now going to be completely on the chlorine atom. So that's an example of a bond breaking. We can also have a bond forming. If we start with the hydroxide anion here, and say there's another proton, an H+, somewhere, we can draw these lone pairs traveling to the hydrogen to form a bond between them. We can also have both happening at the same time. If we have this hydroxide and then our hydrochloric acid here, we can have the lone pairs from the oxygen coming to take off the hydrogen from this molecule, and then at the same time this bond between the hydrogen and the chlorine will break to make a new bond between the oxygen and the hydrogen to make water, and then we're left again with just the chloride minus here. So the arrows always start where the electrons are, and they move to where the electrons are going. And it's very important to remember that arrows signify the movement of electrons, not nuclei. So, for example, we cannot draw an arrow from hydrogen to anywhere because there are no electrons there. It doesn't have any lone pairs to move, so we can't draw an arrow from the hydrogen atom. It always has to be from electrons. And then also another thing to note is that double-headed arrows signify the movement of electron pairs. We will talk a little bit later about single-headed arrows if we're talking about single electrons, chemistry with radicals. But for now, we're just going to be focusing on electron pairs. That's the majority of the reactions in organic chemistry. Correspond to electron pairs. Okay, so with that out of the way, and we will get plenty of more practice using this sort of curved arrow notation, like I said, as the course goes on. Let's talk a little bit about some definitions of acids and bases. First, we have the Bronsted-Lowry definitions. So a Bronsted-Lowry acid is defined as a proton donor. So something like HCl or acetic acid, which is CH3COOH, or sometimes water. They all have an extra hydrogen that they are willing in many situations to give off to a different species. And conversely, a Bronsted-Lowry base is a proton acceptor. Such as ammonia. And I'm going to draw the lone pair in to show that it is able to accept a proton. Or OH minus. It also has an extra lone pair. That's 3 lone pairs. And also in some cases water. So water can act both as a base and as an acid. And we call that amphoteric. And there are several species like that that we will encounter in this course. Let's start a new page here. So lots and lots of reactions in organic chemistry can be viewed through a sort of acid-base lens, if you will. Acid-base reactions are incredibly useful to understand in organic chemistry, and we'll be using this sort of paradigm in many future videos. So if we can draw sort of a general reaction, if we have a general Bronsted-Lowry acid HA, where A can be any sort of counter ion attached to that hydrogen, and say we put it in a solution of water, this is going to be an equilibrium where the HA, the acid, is going to donate a proton to the water and leave behind that conjugate base, A minus. And we can draw this sort of, if we want to draw it with curved arrow notation, to get a little practice in. And we can say maybe A has some lone pairs as well. We can draw this oxygen lone pair going to attack the hydrogen to pull it off. And then at the same time, this bond between the H and the A will break, going to that A minus. And then we have our double-headed equilibrium arrow here. And that gives us our H3O plus. It's our hydronium with a plus charge on it. Let me draw that a little bit better. Plus our A minus. And like we discussed in the previous video, we can write an equilibrium expression for this with our big K, and that's going to equal, remember, products over reactants. So we have H3O plus, the concentration of that, times the concentration of A minus, divided by concentration of the acid itself, HA, and water. So this is very useful, but something that's even a little bit more useful is called Ka, and this is our acid dissociation constant. And this is going to be very useful in telling us the strength of certain acids or bases. And what this is going to equal is just K that we defined just now times the concentration of water. Because if we're talking about dilute solutions, relatively dilute solutions, which is what we're going to be working with most of the time, water is going to have a basically constant concentration because we assume that there's so little acid dissolved in our water that, again, water is going to be basically constant concentration. So we don't have to worry about changing concentration. So that gives us Ka is equal to H3O plus times concentration of A minus, just divided by concentration of the associated acid, HA. And remember from our discussion about equilibrium, if Ka is very large, or K is very large, so if Ka is much greater than 1, we're going to have lots of products. So we're going to basically dissociate all of our HA into H3O plus and A minus. That's going to give us a strong acid. And conversely, if Ka is much less than 1, then HA will not really dissociate that much. It won't react very much. We end up with a weak acid. So what we have to quantify that even more is something called pKa, which we will be discussing at length throughout all of these videos when we talk about different functional groups, different reactions, things like that. That's going to be equal to the minus log of Ka. And I won't be asking you to do any sort of quantitative measurements or calculations with these. It will be mostly qualitative, mostly comparative discussions that we'll be doing, where we will compare pKa values between different species, different molecules, but I will never ask you to determine the pKa given a set of measurements or something like that. That's more of a focus of maybe a general chemistry or analytical chemistry course. So because pKa is the minus log of Ka, if we have pKa very large, well, let's start with very small first. pKa very small, so maybe less than 7. We're going to have a pretty strong, like a stronger acid. You know what, I'm going to refrain from quantifying this because, like I said, we're going to be doing a lot of comparative measurements. So it's not super important to think about whether it's less than a certain number or greater than a certain number. We're just going to say smaller, you have a stronger acid. And if pKa is very large, we have a weaker acid. And remember, that relates directly to the Ka values. If Ka is much greater than 1, and you take the log of that and then multiply it by -1, you're going to get a smaller value for pKa. So, to give some examples, we'll have this reaction right here. If we have water and methanol, CH3OH, our acidic protons are going to be these. And remember, this is going to be an equilibrium reaction. And let's say, hypothetically, it might go to H3O+ and CH3O-. So we can identify the acids here. The acid is going to be whatever is donating the proton, remember. So this will be our acid on this side of the reaction because it's donating the proton to the water. And on this side, our hydronium, H3O+, will be the acid because it's donating the proton to the CH3O- on this side of the reaction. So what we can do is compare the pKa values of these two acids. The pKa of an alcohol is about 16, somewhere around there. The pKa of H3O+ is just about -2. So remember what we said is that a smaller pKa value signifies a much stronger acid. So H3O+ is going to be a stronger acid in this case than the methanol. And what I always remember is survival of the weakest. So maybe that's a little bit funny, but it really helps us understand which direction the equilibrium will lie in these sorts of acid-base reactions. So the equilibrium is going to lie much closer to the left side. So let's draw a small arrow in the right direction and a big arrow in the left direction. Because our weaker acid, whatever has the larger pKa, is going to be the side that dominates in this reaction. So our left side has the weaker acid, the CH3OH, so our equilibrium will lie towards the left. So now we can discuss some factors that might affect the acidity of certain compounds or certain species. And these will be very useful to remember and to understand as the course goes on. Because like I said, acid-base reactions form a really large part of organic chemistry, and we'll be focusing on them in the future. So it'll be useful to understand what makes something more acidic than something else, or what makes something more basic than something else. So we have a few different factors. First is electronegativity. Let's switch colors here. So if we have a couple different, we can imagine acids. So CH4, I've written all the H's at the beginning now, just for clarity. So methane, we have methane, ammonia, water, and hydrogen fluoride or hydrofluoric acid. So that should give you a hint. HF is an acid. So we're actually going to increase in acidity in this direction. And we're looking at atoms within a particular period of the periodic table. And as we increase the electronegativity, we're increasing the acidity. Oops, more electronegative. And you can think of that as for example, HF, there's going to be a large dipole moment, like we discussed in previous videos, in this direction, towards the fluorine. It's more electronegative, and that's going to form a very polar bond. And because that bond is so polar, it's going to be very easy to pull the hydrogen off. It's much more comfortable being H plus and F minus. Whereas in methane, CH4, the bonds are not very polar, and it's going to be very, very difficult to pull that hydrogen off. Another factor we have is size. So now if we look at acids within a group, HF, HCl, HBr, and maybe HI. We also have increasing see if I can write down here close to the bottom, increasing acidity. Because these larger atoms, like iodine and bromine, are going to be more polarizable. So they have a huge electron cloud where you can really push those electrons to one side without much issue. And that's going to make a weaker bond to the hydrogen. We can imagine HF. Maybe this electron cloud is like this. And H here, let's draw a more molecular orbital type thing. HF might look like that, where the electrons are. And HI might look something like this, where all these electrons are distributed so far from the hydrogen and so far from the bond that it's going to make a much weaker bond to hydrogen, and therefore a much stronger acid. I'm going to clarify here that more acidic is usually one of two things. Usually a weaker bond to H, so it means it's more willing to give up that hydrogen, or a stable conjugate base. And we'll talk about that in a second. All right. So our third factor is the S character of molecular orbitals. And if you're a little bit rusty on molecular orbitals, take a look at my video on molecular orbitals and hybrid orbitals in organic molecules. So if we have a couple different compounds here, we have ethane with a single bond between two carbons. We have ethylene here, which is a double bond between those two carbons. And then finally acetylene with a triple bond. Remember that these are hybridized as sp3 carbons, sp2 carbons, and sp. So what does the S character mean? Well, we can think of it as just the percentage of this molecular hybrid orbital that is due to the s orbital. So this is 25%. So 1 part s, 3 parts p, and one of those 4 is s, so 25%. Maybe 33%, about 1/3, and then 1/2 s. And this is actually going to increase the acidity again. And we can say that more S character holds the electrons much closer to those carbon atoms. And remember, if the electrons are farther away from the hydrogen, and they're not really spent, the electrons are not trying as hard, you can think about it. They're not trying as hard to bond to the hydrogen. That means it's going to be easier to take that hydrogen off, and therefore a stronger acid. So again, the increased S character, so such as the triple bonds in acetylene, make those stronger acids. We can also have, sorry, this is number 3, although these aren't in any particular order. We also have inductive effects. And induction is similar to what we've been talking about, moving electron density away from a certain place or towards another place. So if maybe we have a set of, if we can imagine a set of acids here, H3C, CH2OH. So this is ethanol, or drinking alcohol, less acidic than maybe this variant. And then finally, less acidic than the trifluorinated alcohol here. So as we add these fluorines, we get, again, increased acidity. And very highly electronegative atoms will pull electron density away from that OH bond, or away from whatever acidic bond we have. In this case, it's the OH bond is what we're going to break in the case of an acid. Those electronegative atoms pull electron density away from the hydrogen, and therefore make it easier, again, to pull off the hydrogen and make it into an acid. So something like acetic acid, like we find in vinegar, is a weak acid, but it's relatively acidic. But if we add a whole bunch of fluorine atoms and we make something called trifluoroacetic acid, just like we have here with these fluorinated alcohols here, if we add a whole bunch of fluorine atoms, remember fluorine is the most electronegative element, then it gets to be much more acidic and actually closer to the acidity of something like hydrochloric acid, which is a very strong acid. Okay, the last factor we'll talk about is resonance. And this will be more important again as the course goes on. more resonance structures are going to contribute to a stronger acid overall. So if we have CH3OH, methanol again, it's going to be less acidic than acetic acid, and this is going to be even less acidic than sulfuric acid, which looks like that. So resonance, like I said, resonance in the conjugate base this time makes it more stable. Remember, we talked about resonance is going to add stability to whatever molecule or species you're looking at. And this time it's going to make the acid into a stronger acid. So CH3OH, we can't really draw any resonance structures for that. None that are really chemically meaningful. Let's get rid of this little angle bracket. Okay, so acetic acid, what's our conjugate base? It's going to be, our conjugate base, remember, is what we have when we take off the hydrogen. So if we take off that hydrogen, we have a minus charge on this oxygen. We can draw another resonance structure. We can move these electrons down and then move these back up again. So that gives us one resonance structure. And that's going to add a little bit of stability and make this into a stronger acid. For sulfuric acid, our conjugate base, let's draw. So if we just take one of the hydrogens off, then we're left with this minus charge here. And now we can draw a couple of different resonance structures, right? Let's take those electrons up here. Now this oxygen on the bottom is going to hold the minus charge. And if you're having trouble drawing resonance structures, or if you'd like more practice, go ahead and take a look at some of my other videos discussing resonance. And we can, again, take these down, swing those electrons up. Now we get this oxygen on top holding the minus charge. So now we have even more resonance structures, 3 resonance structures this time, which is going to make that into an even stronger acid. Okay, so that's the factors that affect acidity. I'm going to talk a little bit about another definition of acids, Lewis acids and Lewis bases. So Lewis acids usually have an empty electron, an empty valence shell, or an empty orbital where they can accept electrons. Empty shell. So things like BF3. I'm going to not draw the lone pairs on the fluorines, but boron doesn't have any lone pairs. So it has an empty orbital right here where it can accept electrons. Also something like aluminum trichloride. It's very, very similar. Aluminum also has an empty orbital. It only has a sextet. And that means it can accept a pair of electrons. Lewis bases are, if you can guess, electron paired donors. just the opposite. So something like ammonia has this lone pair that it can donate, as well as maybe something very similar like phosphine, pH3, also has another lone pair like this. And those can donate the electrons. Say if we maybe have AlCl3 over here, we can use our curved arrow notation to have those electrons from the phosphorus go to the empty orbital on the aluminum, because the aluminum has a sextet, so it can accept a pair of electrons. And we can form this bond. So that this would be a Lewis acid-base reaction. And if we make sure our formal charges are included, we have plus here and minus on the aluminum. So we will discuss Lewis acids and bases as well later in the course, but they're very useful to understand and to understand where they come from, how they work, and how they're different and similar to Bronsted-Lowry acids and bases, which remember involve protons. So the definition of Bronsted-Lowry acids and bases involves proton acceptors or donors, whereas Lewis acids and bases are all about electron pairs. The very last thing I'll talk about before I finish up this video are nucleophiles and electrophiles. So, if you've brushed up on your roots, remember that phile means lover. So a nucleophile is lover of a nucleus. So this is nucleus loving. Remember, positive charge. Nuclei are positively charged. So these are going to be species with extra electrons. Or extra electron pairs that they're willing to donate. So, very similar to Lewis bases. Things like I- has all of these electron pairs around it. It's a full octet. Or even something like methanol, which has 2 electron pairs around the oxygen. So that could be also considered a nucleophile. It has those electron pairs on the oxygen that in many situations it's willing to give up to a different species. Electrophiles, on the other hand, are again the opposite, like we've been using a lot of opposites in this video. Electron loving. And this would be minus charged, negatively charged. So species that love electrons are going to be very similar to Lewis acids. So empty orbitals or polar bonds. So something like BF3 could be an electrophile, like we talked about with Lewis acids, because it has an empty orbital, so it's willing to accept electrons. Or maybe something like methyl bromide, which is going to have a dipole moment, like we've talked about before, because bromine is more electronegative. So it's going to form a partial negative charge on the bromine and a partial positive charge on the carbon. So that could also be an electrophile. The carbon is going to be, we say, electrophilic, because it has a positive charge, so it's willing to accept something negatively charged, like an electron pair. And we'll talk about these in much detail in the future. Okay, that concludes my video on acids and bases, and a little tiny bit of discussion on nucleophiles and electrophiles. Again, thank you for coming to Total Organic Chemistry. Be sure to subscribe and check out my Patreon page, which will be linked in the description, and that really helps us continue to make content and create videos for you. My next video will be an introduction to alkanes and their properties and reactions.